My today's video will be on the analysis of the transistor amplifier circuit parameters using the H parameter model. We have already discussed the various H parameters which are used to determine the performance of the transistor, or which are specified by the manufacturer for the transistor analysis. So the four important H parameters are HI, HO, HR and HF. So I'm not using the subscript for any of the transistor configurations because we are just discussing it in the general, irrespective of the configuration of the transistor. Now let us consider here I have shown as a two-port network to transistor circuit, wherein I am like we are supposing that it acts as an amplifier circuit, but in order to complete the circuit we need to have an input resistance, which is input source voltage, which is the Vs, with its source resistance, that is Rs. If the voltage source is ideal, then obviously there will be no source resistance. So this source voltage is connected at the input side because obviously the input signal has to come from somewhere, and at the output we are connecting the load resistance, which is RL. Okay, V1 and V2, these are the voltages which are appearing at the input and the output terminals, and the same circuit we can represent it in terms of the H parameters like this, which is shown just below. I've drawn it prior to the making the video, so that you people can better understand it. So the transistor equivalent using the H parameter model is same. You can check it that it is the same, and then after making the internal H parameter model, I have connected the external source resistance, external source voltage and the external load resistance. So the performance parameters which we need to evaluate when we are using transistor as an amplifier circuit, it can be the current gain, it is the voltage gain, the input impedance, the output admittance, and the power gain. So these are the parameters which can be evaluated and which are important. Right. So now let us take each of these performance parameters one by one. So we are starting with the first parameter, which is the current gain. And one more thing, we have made the input terminals, we have labeled them as 1 1 dash and the output terminals as 2 2 dash. So now what is the gain? I have already told you that gain is simply the output by the input. So the current gain is obviously the output current, that is IL, by your input current, which is your I1. Okay, but you see that IL is in the outward direction, whereas the I2 is in the inward direction. So IL will be minus of I2. So it can also be written as minus I2 by I1 because IL is negative of I2. Alright, now so whether you have IL by I1 or minus I2 by I1, that is going to give you the current gain. Now let us take a look at the output circuit, wherein we say we have already made these equations, that is I2 is equal to HF into I1 plus V2 into HO. Okay, now we know that V2 is equal to IL into RL, or it is also equal to minus I2 into RL, because V2 is the voltage which appears across the load resistor RL. Since the current is the same, I2 and IL, only they are opposite in the direction. So instead of V2, we can write in this equation HF into I1 minus I2 RL into HO. Okay, then next step what we'll do is we will transpose the I2 to left hand side, that is I2 plus I2 RL into HO will be equal to HF into I1, and simply we'll take I2 as common from here. It will be 1 plus HO into RL equals to HF into I1. Now I2 by I1 will be equal to HF upon 1 plus HO into RL. So now you have got the value of the ratio of I2 by I1. So this implies that our current gain AI will be equal to I2 by I1 but with a negative sign. So it will be minus HF upon 1 plus HO into RL. Now, what should be the condition that AI will be equal to minus HF? AI will become equal to minus HF when the denominator is 1. This means denominator can be 1 if RL is 0. I'll write if because this is a condition. If RL is 0 or HO into RL is much smaller than 1 so that it can be neglected, then only AI will be equal to minus HF. So this is the first parameter. So this is the first parameter which we have found out using the H parameter model, that is the current gain. Next parameter which we'll take up is the input impedance. Input impedance is the impedance which is obtained seen looking into the circuit from the input terminals. So the input terminals here are 1 and 1 dash, and therefore the input impedance will be this Zi, which will be obtained if we look into the circuit from the terminals 1 and 1 dash. All right, so the previous equation will be helpful to us. So input impedance, let us denote it by Zi, input impedance, denoted by Zi. Okay, take a look at the input circuit and apply KVL to the input circuit first. Okay, so the input circuit where we need to apply the KVL is this. Okay, right. Okay, so you already know that Zi input impedance will be equal to V1 by I1. So find out this ratio and see. Now after applying KVL to the input circuit, we will get that voltage V1 will be equal to the current multiplied by the resistance, that is voltage drop across H1, plus the voltage source of HR into V2. So we can write V1 is equivalent to HI into I1 plus HR into V2. Alright, now we also know from the previous equation that V2 is equivalent to minus I2 into RL. Okay, it is equal to minus I2 into RL, or we can see from the this you see here if I write it as AI, you know that also V2 is equivalent to this, and also we can write AI is equal to minus I2 by I1. So this means your I2 or minus I2 will be equal to AI into I1, that is the current gain, into I1. So we'll use these two formulas and substitute them in equation third. We'll get V1 is equivalent to HI into I1 plus HR as it is. V2 is minus I2 into RL, but minus I2 is AI I1. So we need to write plus HR AI I1, alright, because we have substituted V2 and RL. Okay, so we'll take I1 as common and we'll write HI plus HR AI into RL. So the ratio which will come for the input impedance V1 by I1 will be HI plus HR AI into RL. Okay. So into this, so this is actually your Zi, input impedance Zi. So using the formula from equation 2, which says that AI is equivalent to minus HF upon 1 plus HO into RL. So you will write Zi is equal to HI plus HR into minus HF RL upon 1 plus HO into RL. Alright, so this will be Zi is equal to Hi minus HF HR into RL upon 1 plus HO into RL. Okay? Yeah. So this is the formula, actual formula for the input impedance. However, the second term is becomes very small. The second term is small, and this implies that Zi is almost equal to Hi. Zi is almost equal to Hi. So this is the formula for the input impedance. If the input impedance is, if input circuit contains only resistance, so the input impedance will be a pure resistance. Now the third parameter to evaluate will be the voltage gain. We found out the current gain, we found out the input impedance. Now it will be the voltage gain given by AV. AV is obviously V2 by V1. We are not taking the source voltage, that is Vs, into account first. We are only finding out the internal voltage gain, that is V2 by V1. Okay, voltage gain of the transistor only. Okay, now how to proceed is V2, you know, V2 is equivalent to minus I2 RL upon V1. Okay, and I2 can be written in terms of the current gain as it is AI into I1. Sorry, I have to write it as a subscriptor. A AI into I1 into RL upon V1. Okay, so if you know AI from the formula, which you already have, minus HF upon 1 plus HO into RL, you can find out the voltage gain. Okay, it can also be written as I1 by V1, because you know that V1 by I1 is Zi, that is input impedance. It can be written as AI into RL upon Zin. So Zin is known from equation, let us call this equation fourth. Let us call this as equation fourth, this or this. So Zi is known from equation fourth. So AI can be found from equation 2 and Zin from equation 4, and therefore voltage gain can be calculated. Now we have to find out all same the voltage gain, but taking the source voltage into account. So taking the source voltage into account, it means voltage gain is output voltage by the source voltage, that is Vs. We can break it as V2 upon V1 into V1 upon Vs. Doesn't make a difference because V1 and V1 will again be cancelled out, and we can find it out. Now what is V2 by V1? V2 by V1 is this internal voltage gain. So replacing it by the internal voltage gain and V1 by Vs. Now we need to find out the ratio, this V1 by Vs. So what we'll do is, in order to find out V1 by Vs, because it appears in the input side of the transistor, V1 is the voltage at the terminals 1, 1 dash, and Vs is the source voltage. So this input side will be represented by the Thevenin's equivalent circuit. Okay. So what we'll do is, in order to find out, so we write that in order to find V1 by Vs, replace the input circuit with its Thevenin equivalent circuit. Okay. So let us replace it by the Thevenin's equivalent circuit. Thevenin's equivalent circuit is that you can replace the circuit with a voltage source in series with a resistance. Now let us replace it like this. Rs is the source resistance, and this total resistance of the input part of the circuit is represented by Zi. Alright. So V1 is the voltage which is appearing at the input terminals 1 1 dash. Okay. Now we need to find out V1 by Vs. So V1 by Vs is equivalent to, as per the Thevenin's equivalent circuit, that is the voltage across the resistance Zi will be equal to Zi upon total resistance, that is Zi plus Rs. So this is the Thevenin's equivalent. Now, you know the ratio V1 by Vs. Thereby, we can find out AVs as AV into Zi divided by Zi plus Rs. Again, we know that what is AV equal to in terms of AI? AV is in terms of AI is AI into RL divided by Zi, okay, into Zi divided by Zi plus Rs. Now you'll be surprised like wherein we got this AV replaced by AI into RL. So it is this equation, this one, AI into RL divided by Zn. So let us keep it here and try to try to cancel out this Zi with this Zi. Okay, so what is left will be AI into RL upon Zi plus Rs. Okay, now AI into RL. Now what if Rs is 0? What if Rs is 0? That means if you have an ideal voltage source, Rs is 0, then your AVs will come out to be AI into RL upon Zi. So can you check from the formula AI into RL divided by Zs? So it will be the same as AV. That means AVs will be equal to AV only if Rs is 0. But if Rs is equal to Zi, then AVs will be equal to AI into RL upon Zi plus Zi. So that is AI into RL by 2 Zi. So that is 0.5 AV. So it says that if Rs equals to Zi, then voltage gain reduces. So as Rs increases, AVs decreases. Alright. So this is our voltage gain, internal voltage gain, as well as the voltage gain taking into account the input voltage source. Now using the same method, let us find the current gain, AIS. AIS is simply IL by IS. It is I minus I2 by IS. It can be minus I2 by I1. It can be broken down as into I1 by IS. So we know that I2 by I1 we have already found it is equal to AI. into I1 upon Is. So now I1 is in the internal part of the circuit, that is the input part of the circuit. Internal part, no, input part to be precise. And Is is also in the input part. It is the source current. Now, in order to find out I1 by Is, we have to replace the input circuit by the Norton's equivalent. That is using the Norton's theorem. So we'll write that in order to find I1 by Is, replace input circuit by Norton's equivalent. Okay. Now Norton's equivalent says that you can replace, you can have a current, you can take it as a current source, and all of the resistances come in shunt with the current source. So the input current which you have is Is, and the resistance is Rs. The resistance Rs comes in shunt with Zi. Zi is the input impedance, Rs is here, alright, and this is here. Okay, so the current which is flowing here is I1. Okay, so the Norton's equivalent theorem says that the current flowing through the resistance path I1 will be equal to the current flowing through the opposite side, that is Is, and the resistance of the opposite branch, that is Rs, divided by the total resistance, that is Rs plus Zi. So it will be I1, if I take Is here, so it will be I1 by Is equals to Rs upon Rs plus Zi. Very simple. And we will find the formula AIS as minus AI into Rs upon Rs plus Zi. Okay. Now from here we can further simplify it as AI into Rs divided by Rs. We can take it as common, 1 plus Zi by Rs. So we can cancel out this Rs with this Rs, and we will get minus AI upon 1 plus Zi upon Rs. Alright. Now when will be this total current gain, including the source, external source voltage, equal to the internal current gain? It will be equal if Zi by Rs is equal to 0, which will happen only, this thing will happen only if Rs is infinity.